Okay, hello everyone. I'm Sarah. Most of you probably already know me by now. So I'm going to start off by showing the demo which I released 2 weeks ago now. So this is pretty new. So it's Archimedes demos and me. So I'll be talking about the demo you've just seen, Reach, as well as last year's demo, Horizon. So a little bit about that person I am. So I first got Beeb in late 1990. I was 3. We moved to PCs 3 years later, so I never actually had an Archimedes back in the day. So why I'm so interested in them now, I've got no idea. I started writing emulators in 2001, starting with BM. Arculators then started later that year, but as I was 14 and didn't know what it was I was doing, it wasn't until 2005 that it actually became usable. And I've also written various BBC games, lots of music conversions that I suspect only I listen to, and I also did write one full demo, imaginatively called Demo 128, back in 2011, I think. But I've never really done much, written much on the Arc, just simulated it. So why did I do this slightly strange thing? Well, basic reason is, if you've been attending ABug in the last couple of years, you may have seen me at various points fixing an A3000. And once I got it working, I felt I should write something to run on it. Demo seemed like not a bad idea. And then, so that was why Horizon started. Reach got started because at the party at which Horizon was released, I bought an Archimedes 410 with an ARM3. So I thought, let's try an ARM3 demo. And part of the other reason for doing this is there's not actually a lot of competition for writing our demos on this platform. So there was an Acorn scene in the 90s that wasn't that big. It pretty much died off in 2001. And the only demos released between then and Horizon in 2019 were ports from other platforms. So the demos written for STL, which were released on everything. And so part of this was I was interested to see if I could kind of resurrect some kind of scene interest in the Archimedes. Because I mean, there's still demos being written for Amigas, Atari STs, C64s and the like. So why not the Arc? So the two demos I've done. So Horizon, the original party version, which you can read beta, was released at Nova 2019, and the actual proper final version was a few months later. And it's basically targeting an A3000 spec, so it's ARM208 MHz, 2 meg of RAM. And then Reach, which was released 2 weeks ago, was released at Nova 2020, and that's targeting an ARM3 at 25 MHz with 2 meg of RAM. So development tools, I prototyped a lot of the effects on the PC in C because it's, you know, it's something I know reasonably well. For the actual Acorn side, it's obviously everything's this in an assembler because that's how you get performance. But I use Arculator to host everything. Then use Zap as my editor, ASM for assembler, and use a linker and a couple of other things from the Acorn desktop development environment. So at this point, everything goes very technical. So if you're not au fait in ARM assembly, you might want to go and do the ironing or something for a bit, because otherwise you may not follow too much. But in any case, let's dive into what I actually have to work with on the Archimedes. So go straight in the deep end. Instruction timings. So the ARM2 is nominally pipelined, so we can get one instruction per cycle. And so for your data processing instructions, we work entirely in registers, things like add, subtract, and, or, those are all single cycle. Memory instructions are a lot slower. So a single register load or store on the ARM2 is 4 cycles. Load multiple, load and store multiple, so use multiple registers in one instruction. They can go a bit quicker. So technically 1 cycle per register plus 1 cycle per 4-word boundary you cross, because that's how the DRAM controller works. So I put 1.25 cycles there. Branching is about 4 cycles, I think. Again, that's going to depend on DRAM control, DRAM alignment again. Multipliers are actually quite good for the era. So the multiplier runs 2 bits per cycle, so you get with 1 cycle overhead. So your maximum length is 17, but there's an early out algorithm. So if it runs out of bits to process, it will terminate early. So it can go as low as 2 cycles, which is helpful. The DRAM controller adds another cycle every 4 words or so. which affects all instructions. And it's a shared memory system, so everything except the multipliers will get stored if you have video or sound DMA kicking in. So there's some implications which come out of this. Firstly, unroll all the loops. Loop unrolling is very beneficial on ARM2 because you can get rid of the overhead and there's no penalties having large code. You're also generating code on the fly or at load time. Again, since there's no size penalties, you might as well if it's beneficial. Lookup tables can be helpful. It depends on how expensive the whatever code it's replacing is, but I mean, a lookup is 4 cycles. If generating the result would take more than 4 cycles, then it's a win. And aligning code and data is quite important. So it's beneficial to have things like your loop starts on forward boundaries. Data starts on forward boundaries as well. You free up a few cycles that way. So that was all the relevant stuff for demo 1. And demo 2 moved to ARM3 and things are a little different. So if you don't touch memory, everything's good. It's all the same as ARM2, except you don't get the DRAM penalties. LDR, if you hit the cache, it's still 3 cycles, which is a pain. If you're on a 486 or something, it would be 1 cycle. But this is ARM3, so we've got 3 cycles. Load multiple, if you hit the cache, 1 cycle per register, plus you get the 2 cycle overhead. Branching's down to 3 cycles, again assuming everything's in cache. Stores are kind of bad. It's a write through cache and you've got no kind of store buffer or anything else to try and accelerate stores, so you go straight to main memory. And so it depends on the speed of your memory system. It's 8 or 12 depending on which machine you're on. So best case, a single register store is about 8 cycles. Worst case, going to be more like 16. And store multiple has similar awful performance. So yeah, I mean, things are, except for stores, things are generally great if you can stay in the cache, but you've only got 4K of it. And to put things in context, a 64 by 64 pixel texture is 4K. So you can get one of those in your cache. And it's also unified cache, so it's shared between code and data. So if you've got this hypothetical texture, you don't have any room for instructions. So you're going to be fighting between the two, which costs performance. And the cache miss, it's going to fetch 4 words, and that's going to be between, again, depending on memory speed, between about 14 and 21 cycles every time that happens. So try not to make that happen too often. And so cache misses and stores will be stored by DMA. Thankfully, if you're hitting the cache, then the ARM3 is intelligent enough to not stall. So compared to the ARM2 ones, so on the ARM2, unrolling everything is beneficial. On ARM3, don't unroll anything. You don't have the cache for it. So the general obvious rule is try and keep your inner loops plus your working data set below 4K. That way you should get a reasonable hit rate on the cache. On the ARM2, aligning everything to forward boundaries was beneficial. On ARM3, don't do that if it means you're going to miss on the cache. There's a pattern in this. So generated code will perform badly because it tends to be very big. If your code doesn't fit in the cache, then you're going to be down at ARM2 type speeds, regardless of how fast your ARM3 is clocked. So again, best not to do. Lookup tables obviously have penalties if they miss the cache. So either they're small, so they hit the cache, or they're very sparsely accessed, so you only access a few words. So you don't have to pull the whole thing into cache. And since stores are so expensive, try to merge stores as much as possible so you pay the penalty as little as possible. And the more generic things which apply on both CPUs. Since you've gotten early out on the multiply, try and drop the resolution of any of your operands so that you can take advantage of that. And also don't multiply negative numbers if you can avoid it, because it's an unsigned multiply, and the early out doesn't notice that your result is your operand is -1. It just sees FFFFF. So if you can work around that, that's often beneficial. Remember to use a shifter. I forget, because I often forget it's there, and 3. And try to keep everything registered as much as possible. You've got 16 registers. This doesn't last as long as you actually think it might. So I've often found things like packing multiple values into a single register, where possible, will help here quite a lot, because falling back to memory is quite expensive. I'm sure anyone who's coding 602 will be playing a very small violin at this point. So that's the CPU side. Video. For the most part, the video system is very sensible. It's just a straight bitmap, except that the palette is a bit rubbish on the old VidC. So in the 16 color modes, you can freely define all your colors, which is nice, but 16 often isn't enough. So in many cases, I've had to drop to 16 colors to get decent lighting, and with a configurable palette, but you end up not being able. You end up with monochrome lighting effectively. So in many cases, you have to go to 256, and it's not fully configurable because you've only got 16 palette registers to cover 256 colors. So the way they've implemented this is that the top 4 bits for the physical color are taken straight from the top 4 bits of the logical color. So the top bits of red, green, and blue, they're all fixed in hardware. You can't change them. The rest you can change, but that means you're effectively tinting, in Acorn's terms, tinting an existing 16 color palette rather than actually defining proper colors. So one of the things this means is you can't set up any decent gradients. So not in terms of you don't have the color resolution, and they're not organized in a linear fashion. The actual color numbers are all determined by hardware. So to make anything look good, you have to use a lot of dithering. You use a lot of color lookups, and that tends to also slow things down a bit and make everything look a bit rubbish, which is slightly irritating. But if I didn't want irritating things, I would have chosen another platform. More things on video. It's a shared memory system. Video is cycle stealing from the CPU, and the bigger video modes eat more bandwidth. So something like mode 9, which is 320 by 256, 16 colors, is reasonable. You go ahead to mode 15, which is 640 wide with 256 colors. That will eat a lot of your CPU. And then since we're not in the 80s anymore, VGA support is somewhat required, and it's a complete nightmare. There's no hardware. There's not really any hardware support for it. You need to do line doubling in software, which is painful. The VGA modes are all 480 lines, so they use more bandwidth and more memory. And whatever your plotting function is, it either needs to write everything twice, or you need to do a line doubling post-process. And in both cases, that's again going to eat more CPU time. And just to add insult to injury, the refresh rate is higher at 60 Hz, which is all fun to deal with. So on to some effect type stuff. So most of the effects in both demos are essentially basic 3D engines. So anyone who's written a 3D engine, most of these steps are going to look reasonably familiar. So you have to transform vertices, you have to light them, you have to project them onto the 2D screen, you then do backface culling, you then do clipping, and then you actually finally get to plot something. And so all these steps are fun to implement. So we start with transform, which is, in my case, almost always a 3x3 rotation matrix. It's a decent article on Wikipedia if anyone needs to read up on that. Your main issue is that you don't have enough registers to do this entirely efficiently. So I toss this up. You effectively need to have 18 registers. You've got 16. It doesn't fit. So you see a few workarounds, and I've done several different ones across various effects. I think in Horizon, I tended to spill some of the matrix onto the stack, and then you have to reload it during you're in the loop, which is not ideal. One nice trick I discovered was to use the stack as a destination pointer. So you effectively push all your destination vertices back onto the stack, and hope you don't run out of stack, because that's often quite a lot of data. Another one method was to sort all your vertices by one axis and then pre-process that axis outside of the loop. It also reduces the number of multipliers you have to do, so it's quite a useful optimization. And since I promised this was going to be technical, you can have some code. So this starts with the last method I mentioned. Does it? No, it doesn't. That's a complete lie. This is actually a different one where we pull in and transform two vertices, and then once we've freed up a register, we go and pull in the third and then handle that separately. And to make things even more fun, I've had to at one point pack the remaining loop counter and the source pointer into the same register at one point, and then unpack them before trying to process the next iteration of the loop, which makes things fun. But it seems to work, and it seems to be tolerably quick. There's much else to say here. Other than that, I spotted embarrassingly, there is actually a move instruction, which isn't necessary, but I think in this effect, transform wasn't the main bottleneck, so not as vital as it might have been. So once you've got your vertices, you can do some basic lighting. For the most part, we just stick to regular diffuse lighting, where we have have a light source at infinite distance, like the sun or something, where it has a fixed direction vector no matter where on the object you're looking at. And so what we do is a dot product, which is basically just more multiplies against the vertex normal, which was pre-calculated earlier on, baked into the source data, and was then transformed with all the actual vertices. And then the dot product gives us an intensity, which we can then feed into the plotter. And in some effects, I tend to fake some specular highlights. That's just by having a section of the palette which goes to white rather than. So you start out at black, go to the object color for most of it, and then at the very end fades towards white, and that makes it look slightly prettier. Though in one effect, we did actually have real specular lighting, which is it's a more complicated step where we take the light vector, we reflect it around the vertex normal, and then do a dot product with the camera vector to determine whether it's actually hitting the eye or not. And that gives you some effects, and then that gives you a nice specular highlight and an effect where you can't really see it. But I know it's there, so I thought it was nice to do it really once. Some of the other more basics, some of the other stuff, projection, that's the divide by Z and then multiply it by your display width and height. So the only trick there to divide is done by reciprocal table, is done by multiplying by a reciprocal table, which is faster than having a divide routine. We then have culling, which is based on the which is so at that point you assemble your triangles or whatever object it is out of your vertices, and then you calculate the area, which gives you a result based on whether the destination vertices are wound clockwise or anti-clockwise and then use that to decide whether it's the triangle is actually facing the camera or not. If it's not, you don't draw it. It's mostly clockwise, but I'm not 100% consistent on this. We then do some kind of whole triangle clipping at the extreme edges of the display, and also I think also do near plane clipping at one point. So that's triangles which would go behind the camera, which would do all kinds of fun things, plotting them. And then we do top and bottom clipping just before actually plotting each trapezoid, which is twice per triangle, which isn't too bad. And then there's left-right clipping, which is calculated on every scan line, which is not optimal. But I couldn't be bothered to do any actual maths by the time I implemented this. Plotting, so it's mostly triangles. We have to do some triangle setup to generate gradients for the various edges and for texture and lighting coordinates across the triangle, vertically and horizontally. This code is a complete and total mess, and I'm terrified to modify it. It's also bigger than I'd like. I think it's about 2K, which is half the cache. So we implement the divisions again by multiplying by a reciprocal table. There are some glitches. I've seen similar glitches in a lot of fairly basic software renderers, so I'm not too worried about them. And so this just generates into kind of top half and bottom half trapezoids, which then get past the actual render code. And then the render code, so it tries to write a full word at a time, so it will calculate 4 or 8 pixels in a loop iteration before writing, depending on what screen mode you're in. It's got a separate path for handling spans which are entirely contained in a single word, and Horizon goes further by using lots and lots of generated code. So it will create a span fill routine for every length of line and every start offset within a word, which uses something like 400K of memory or something. Since this doesn't play well with the cache, Reach doesn't bother with any of this and just uses a basic loop. And now in texture mapping, we have to use a load per pixel, which is slow because loads are slow on ARM, because of course they are. To speed things up slightly, and because we're running out of registers, the U and V coordinates are packed into a single register, and then lighting is applied on top of this, which is a bit compromised in various places. So on Reach, it's half res and a lot of effects to try and claw back some performance. Most effects have a lot of dithering in, which unfortunately hurts performance. The actual lighting in mode 9, since we just got a gradient setup in palettes, we can just use a subtract to attenuate the light intensity a bit. This doesn't work on mode 13, so we have a separate texture for every lighting level and select each texture per pixel, which is expensive and means it doesn't cache very well, but it looks slightly better for as good as mode 13 lighting ever can look. And we can have some more code. So there's 3 different routines from different effects. So on the left is a plotter from Horizon, which just does shading with no texturing. It's actually quite proud of this one. It does 2 pixels in parallel by packing 2 different intensity levels into the same register. So that's reasonably efficient. Middle one, that is a mode 9 texture mapped plotter. You can see it's a lot longer because the one on the left does 8 pixels, the one in the middle does 1. It's got a load in the middle. It's got some clamping to deal with a triangle setup bug. It works, it's moderately expensive. but I think it's tolerably well optimized for the CPU, sadly. And then on the right is the mode 13 plotter. And that's 2 pixels, I think. Yes, that's 2 pixels. That's steppingly lighting every other pixel, which is why there's an instruction commented out. And it's doing some lighting selection. It's doing texture selection based on lighting, with a little differing added in. And again, I think, sadly, that's reasonably optimal. I'm hoping there's something obvious I'm missing where there's an instruction or two you could dig out of that, but sadly, I suspect that's about as fast as you're going to get, which is a shame because it's less fast than I'd like, particularly on ARM3. So there's a few more specific examples of this. So one of the effects in Reach has reflection mapping. So in this case, so ideally for sphere mapping, what you're supposed to have is you have basically a fisheye view of the environment surrounding the object. And then based on the normals of each vertex, you can pick where in that fisheye you're going to source the texture from. And so you get a nice kind of view of the object reflecting the environment. There's no actual environment, so I just took the background picture, kind of did a kind of spherizing fisheye effects in GIMP. Kind of tinted it grey a bit more, so the object looks more metallic. And then for the actual coordinates, you just take the vector from the eye, reflect it around the normal, and then effectively kind of bounce that back into where the texture is. And it's certainly far from accurate, but it looks reasonably good in motion. And also, this is in Reach. This is the one piece of competent art. There's one piece of competent art in each demo. This one was done by Forza back in 2011, as I understand it, for an Amiga demo which never happened. But the guys at Desire were quite happy for me to use it here. So I think it works quite well. So moving on to some more effects. This one at the beginning of Horizon, I thought it wasn't a bad effects, and also it's an implementation which really does not cache well at all. So it's incredibly unfriendly to the ARM3. So the line draw routine itself has a nice run length implementation where it calculates the length of, effectively the length of each run within the line, and then it jumps into some massive chunk of generated code to actually plot an entire line with each segment being this length or this length plus 1. So I was quite proud of that. It's very fast. It's quite fast on ARM2. So you can get 168 lines per frame at 50 frames a second, but it really does not like ARM3. So when I was trying to do the VGA port of Horizon, I had to skip the actual line doubling and just have scan lines in this effect because there wasn't enough performance left on an ARM3 machine to do the line doubling, because the effect didn't run fast enough. So the Galaxy effect was another interesting one which uses some of this. So this one was moving 10,000 dots a frame at 25 frames a second. So that's obviously a lot of the vertices to move about, so we cheat a bit. So the Galaxy itself is mirrored twice. So the if you're looking at it so that the kind of circular, if you're looking at it from the side on, so the kind of circular bit is going around the top, then we mirror on the vertical axis up and down, and then on the actual spiral itself, there's also another mirror by flipping everything 180 degrees. So that cuts down the number of transforms by, I think it cuts it in half, but we get to reuse some of the first transform in the second one, I think. I can't quite remember. So And again, this one, this was heavily optimized to fit everything in cache as much as possible. So we groups all the vertices by the y coordinate, which gives us about 70 at a time. So we run in a loop of transforming about 70 and then plotting them, and then so that lets me reuse the same buffer memory for the output vertices, which means we get better cache utilization. And so we also wanted to have a configurable palette, but also needed byte per pixel. And so the workaround I had for this was run in mode 12 and just plot 2 pixels at a time. So that means that we can get the blending done much easier. So for every star that's plotted, we effectively read the pixel currently at that location. We then subtract 1 from it, and then if we've not overflowed, we then write it back. So that means we get kind of a semi-transparent effect, plus we get saturation when there's lots of dots on the screen in any one location. So I thought that looked quite nice. And it was only afterwards, only after I'd written it, I realised I subliminally ripped all the movement of the galaxy from the intro of the Sylvester McCoy era Doctor Who, which I didn't note until after I'd written it. So, but it works reasonably well. So I couldn't be bothered to change it. So going back to Horizon again, there's the sphere plotting effects, which again works reasonably well. So this has for the sphere, rather than doing the actual maths, we've got a nice table for every size of circle, the size of the spans we need to draw and how many. And the codes for plotting the spans again is auto generated again for every length of span and every start offset in the word. And so we can just about get 30 circles after about 50 frames a second on an ARM2. I think this does drop a couple of frames, but it's all triple buffered, so it's not that noticeable. The drops aren't that severe. But the one big cheat is that all the movements is pre-calculated. So all the vertex transform is run during the start of the effect, and then when actually doing plotting, all we do is pick up all the destination vertices from a table, which just saves a bit of time, but does mean there's a pause as the effect starts, which is slightly irritating. The other big one, which I kept reusing, was the Rotozoomer. Both demos have one of these, but they've ended up with very, very different implementations, mainly in the quest to hit 50 frames a second. So it's on very simple basic level. It's texture mapping, but it's texture mapping across the whole screen instead of trying to texture map on triangles. So and you can see some very basic code there. So that's just extracting the U and V texture coordinates, we then load from the texture, and then we just step everything. Just fairly simple, and that's mostly not what was done in Horizon. So Horizon's a 2x2 plotter, so effectively plotting everything at quarter resolution, so it's 160 by 120, I think. And it's a complete cheat. So what I do is I run the routine just been shown for only the first scan line on the screen, and rather than plotting anything, I just note what texture coordinates we would have used on every pixel, and then we reuse those on every line, but with a different start texture position on the left-hand side of the screen. Which gives us something that's approximately right. It looks very bad when it's zoomed into the texture because you get kind of additional pixely layer on top, which is kind of horrible. So I didn't zoom it, so I didn't do any rotation when zoomed in to avoid that. But if you look on I've certainly seen it on some Amiga rotozoomers, where you get this slightly odd effect when the texture is zoomed in, and it's because they're doing some horrible pre-calculation like this. So this involves a lot of self-modifying code, but it lets me get 50 frames a second on an ARM2, so I thought it was a reasonably successful effect. And this also is the effect which has the only piece of competent art in Horizon. So the Acorn Devil was drawn by John Blythe, who I think was doing the Bit Shifters demo at the time, but he kindly quickly did this for me, which was nice. On Reach, we didn't do the same cheating, mainly because there's perspective involved. So as you move down the screen, the texture effectively moves away from the camera. So that means that all the texture offsets are going to change in every line, so the cheat using Horizon doesn't work. But we're targeting a faster CPU, so we can probably afford to do this properly. So this is actually calculating the correct texture coordinates on every line. So no cheating involved. The other thing it does is it implements MIP mapping. So there is the base texture is 32 by 32, but it goes down by every power of 2. So we've got 60 textures at 16 by 16, 8 by 8, and so on. And those are used the further you go away from the camera, the smaller the textures get. That reduces the amount of kind of noisy aliasing you get in the distance, so everything looks a bit smoother. The different levels of texture are also have different brightnesses, so this gives kind of fog effect. So whereas as you go further into the distance, it gets darker. And because the other textures are all smaller, they all fit in the cache base, which is again good for performance. And the base texture is smaller than it was in Horizon, but that's again fit in the cache. So in the final Rotozoomer, the base texture is 1K, which fits nicely. It was originally 4K, but it was missing the frame rate target, so I just cut it down a bit. It's not that noticeable. I think we're almost done now. So the opening thing effect on the on Reach uses a very similar effect. It's mostly the same code, except instead of using the texture as the input, we're using the last frame instead. So that's, I mean, it's basically the same code. The only difference is we're doing a kind of per pixel lookup, so that each pixel, so that every time the fuse frame is red and used as texture, we make it one step darker. So you get kind of nice effects of everything kind of trailing away in the distance. But to hit reasonable frame rate, have to run it at half resolution. The ARM3 is not that good, and this doesn't cache that brilliantly, so it's an acceptable compromise. Just a couple more quick ones. So this one in Horizon, this vertical bar effect, I thought was worth mentioning because it's the only mode 15 effect in the demo. So it's 640 by 256 in 8-bit color. So you get good color resolution out of it. It is basically a memcopy exercise. So all the bar positions when rotated are all pre-calculated, and we just copy the appropriate one for each line. The only problem we've run into this is that on an ARM2, you don't have enough bandwidth really to do this for the full screen. So the effect started out at the full width of the screen, and it kept getting narrower and narrower and narrower as I kind of worked on it. So I think it's on about 2/3, or maybe a little less. But I think it still looks okay, but it's a bit of a filler effect. So towards the end of Reach, you see this nice sphere, which is bump mapped. This is basically an awful lot of dot products. So the sphere itself is an array of normal vectors. We effectively do dot products against the light vector, which is constantly moving in this effect, and it makes the sphere look bumpy. It's very simple. I think the base resolution is 2 by 2 pixels, but that means we get 50 frames a second, which looks reasonably nice. I think this is the final one. This is the Greetz tunnel from Horizon. So this is a really old kind of demo classic effect. So the tunnel is totally pre-calculated. There's a big table giving the texture coordinate for every pixel in the tunnel. So basically just reading through this pre-calculated array and using that to look up textures. The tunnel appears to move around. That's not doing anything perspective, that's just panning the table around. It's a very cheap effect. This would look odd, but the texture is animated, so it's not quite so noticeable. And that is because this is mode 13. We can't do a palette effect, so this is literally just a bunch of textures just animated in sequence. And then the text is blended on top. There's a lookup table which is trying to blend I think one tunnel pixel with 2 text pixels, but because we're in mode 13, the color resolution isn't really that great, so it ends up looking very dithery. And so the fact it's actually blending probably isn't quite that obvious. So that's all the effects I can bother to talk about. All that I think are interesting. So from the music player, I did write my own for Horizon. It was heavily optimized for ARM2 with a fully unrolled buffer fill routine. It plays back to 15 kilohertz on ARM2 systems. On the final version, if you've got a faster CPU, it will bump up to 31, which will remove some aliasing if your hearing is particularly good. The original party version had a broken replay routine. This wasn't ideal for the musician, but then he did give me the music only the morning of the competition, so I didn't really have time to fix everything. For Reach, I switched, instead of using my own player, I used QTM Player, which has been around for donkey's years. I was originally planning to use mine, but when I got the tune, there were some bugs, and I figured I could either spend 2 days fixing the bugs in my player, or I could spend 2 days playing video games, and I chose the easier option. Just a bit more code. I think this is the last code. This is just what my buffer fill routine looked like. So it's essentially just doing a sample lookup, applying volume through subtraction, which you can do because it's a logarithm, and just incrementing the pointer. Main fun thing about this is that it completely run out of registers. So I think this is running with interrupts disabled, so I can reuse the stack pointer register, which is horrible, but it works and it makes it reasonably quick. A bit of glue code. So there's a main loop at the start of application memory, which just decompresses and runs every effect in turn. Each effect is compressed with a very basic LZ77 type compression, which is basically it can refer back to previous decompressed data. I think the window only goes back to 56 bytes. So it's not, the compression ratio is not great, but it's good enough, and the decompression is fast. I think it's something like 12 instructions long, so it's tiny. And then I have to drop the RISC loss at some point, which I do as little as possible. So some basic event handlers, so we can clean up on errors and then get things like the vsync and the system tick events, and the basic things to set screen mode, to get buffer addresses, do page flipping, that kind of nice basic thing. And so the results of all this, so Horizon was submitted to the old school demo compo at Nova 2019. It came third, behind a BitShifters BBC demo at #1, and Ron Kieran's compo filler demos at #2, which is fine. Reach had exactly the same results the following year, so I think there's a conspiracy going on. Though to be honest, there weren't really many old school demos at either party. I think in total there were 4 this year, 5 previous year. So at Nova, they clearly don't like old school machines very much. Either that or there just aren't enough people there. So quick post-mortem, I think Horizon, this is my first demo which I actually tried to release at a demo party. I think there are some good effects. Texture mapping got applauded when it was shown. It's the only effect to get any audience response whatsoever. The sphere effect seems to be the rotation big sphere seems to go down reasonably well online, and I thought the Go shading objects looked and ran okay, but I don't see much response to that. It does suffer from bad pacing. It's got too many effects. It's too long. There's a great big load right in the middle of the demo, which was painfully long on the big screen. And I did end up having some full screen art, which was drawn by me, which looks terrible, and it gets too much focus in the demo. So the music, as I said, came very late, so this doesn't really synchronize with the demo at all. If we'd had more time, I would have tried to fix that up. And the initial release was basically unfinished. I think I was already 3 or 4 hours behind deadline when I put it out, and yeah, it had issues like the music being out of tune, and the Greetz effect lagging badly, so it wasn't great. Though the final version did improve some of those things a bit. On Reach, I thought things were a bit better. So I think the pacing is much improved. There aren't as many effects. Everything cuts a bit quicker. I got the music 2 days in advance, so I was able to actually synchronize it with the effects a bit. So most of it's just fairly basic, trying to synchronize things on the beat, but it seems to work okay. I didn't have any of my own bad full screen art, which was good, but some of the textures were kind of poor. So I think on the kind of Zarch landscape, the main land texture is literally just the random option in PaintShop Pro. And some of the effects ended up slower than I'd hoped. So the kind of torus and tonal effects were trying to do full screen texture mapping, and the ARM3 is not really up to it. So they're choppy and I'd like. So finally, for in the future, I think I burnt out badly after Reach. I think people around me may have noticed I had a little bit of a breakdown. So I'm probably not going to do another demo on my own of this kind of scale, because it kind of broke me a bit. But there is interest in doing collaboration with various people, mainly bit shifters and Desire, which would help. Which would be good if I could code without having to carry a whole demo myself. I might also look at doing some intros, something that's kind of single effect. I think that could be reasonable. The other good thing I noticed in the last year is that bit shifters, Icebird, and Kreml, I'm not sure how to pronounce that, have released demos on the platform in the last few months. Whether that's me kickstarting anything or not, or if that's a complete coincidence, I don't know, but it's nice to see. And so yeah, that's it. Just over time. Any questions?
Hi, Sarah. It seemed to me that you had a very different experience with the 2 different processors, ARM2 and ARM3. I'm just wondering, I would have thought that ARM3 would have been a little more advanced in some ways, but it seems that you had more trouble with that. Is that right?
More or less, yeah. So I think for ARM3, they made what would be the obvious advance for ARM2 to decouple it from the memory bus by adding a cache, so you can get the clock speeds up. But it's a very simple implementation, and there are quite a number of issues involved getting the performance up. So I mean, on paper, it's 3 times as fast as ARM2. In practice, you have to work quite hard at it.
Thank you.
So, Sarah, do you find that your ARM2 effects will run more happily on the ARM3 with the cache disabled?
They run about the same. So I mean, I think they might be very slightly slower on the ARM3 due to the way it bounces between the fast CPU clock and the slow memory clock every time it has to do a cache fill. But in practice, it's pretty similar performance. Anyone else?
I've got a quick question, Sarah.
Yeah.
So you developed actually inside the emulator, or
Yeah.
Yeah. How did you find that? That sounds quite painful. Or is it?
It's fine. It's better than developing on the real machine would be.
That is true.
I can quite easily pass things in and out of native file system. I can overclock the CPU a bit. So Archimedes got some basic overclocking options, so you can run with faster CPU and faster memory, which is helpful a bit. It's reasonable enough. It gets painful on some effects where there's a lot of inline data, because then the assembler will take forever to process it. But for the most part, it's usable.
Yeah, I've been using VASM as a external assembler, and now the bugs are fixed. It seems to work pretty well. So
it's always good to have the bugs fixed in your assembler.
Yeah.
The one I've got has some bugs when trying to use the ADR macro. When your code gets too big, it starts failing to be able to link to stuff that's right next to it. Not quite figured out what on earth that's about.
Cool, thank you.
Any more questions from anybody? No. Okay. Well, thank you very much, Sarah.
I hope that was interesting and not too dull. I know I'm not a brilliant presenter.
No, I think it was really interesting. Once you understand the limitations of what the demos are working within, they become all the more impressive. I think one of the things with the Archimedes is it's very hard to have a handle on, and even though I've used them on and off for years, have a handle on what the actual capability of the system is. So judging whether something is impressive or not without understanding the limitations of the system becomes very hard.
Yeah, I think in many ways it's not a well understood system even by people who frequently use it. So, I mean, things like, for example, the instruction timings I pointed out there, they're not obvious if you not actually try to go and measure this stuff, and that does impact on performance quite heavily.
Yeah, I agree. I think
I was just going to say, as you've probably found, the palette is the worst thing, though.
Yeah, I'm sticking with 16 colors for now. I'll experiment with 256 later. I was going to say, I think the surprise for me was the limitations of ARM3. You sort of assume that ARM3 is this amazing beast because it's clocked so much higher and it's got a cache, but actually it sounds like a world of pain, whereas ARM2 is just nice and straightforward and much more 6502-like, I guess, which is familiar territory for me at least.
Yeah, I mean, ARM3 is fine if you can fit in the cache and you never store anything. As soon as one of those assumptions is blown, you're going to start having performance issues. The store was the real shock for me when I first started looking into it, because I didn't expect it to be that bad. And I think on the RISC PC systems, when you get to the ARM610 and later, they've put a basic store buffer in, so it's a lot faster. But on the ARM3, it's incredibly slow.
Yeah, you kind of need to store when you're writing to the screen, right?
Yeah. It's sad but true.
It would be quite interesting to see some strong ARM-based demos. I mean, I have two RISC PCs downstairs. I played with them a little bit. One of them is like stock, and the other one I think has been overclocked up to nearly 300 megahertz. It would be really interesting to see what one of those could do, you know, with your coding skill on it, that's for sure.
Well, there are a number of decent strong ARM demos already. that were written in the late 90s. To be honest, I'm not sure I could better those. I mean, the problem you've got in strong ARM is you've got the caching issues of the ARM3, but they're so much worse. Because the process is clocked so much faster, but the memory is not really much faster than it is on an A5000.
Mm-hmm.
But no, there are a handful of reasonable demos for the strong ARM machines out there.
Do you know if anyone's written any demos for RISC-OS running on the Raspberry Pi, just talking about clock speeds?
Because of the what new ones I was talking about that come out recently. I think only the bit shifters one is the only one targeting old hardware. The others are, I think they're size demos, so they're like 256 bytes, but they're targeting Raspberry Pi.
Right. I guess that's almost bare metal programming, though, given RISC-OS.
Effectively, yeah.
Yeah.
Yeah,
Okay.
they're just using RISC-OS just to set screen mode, basically.
Exactly. Cool. It was a good presentation. Thank you.